All right, I'm James Sterbenz at the University of Kansas and a secondary appointment at Lancaster University in the UK. This is joint work with people at Kansas, people at Lancaster, and Deep Medi at UMKC, Zheneng Cao at Hong Kong Polytechnic, and Jin Yang at CU-C Beijing. We have been looking at resilience for quite some time in various pieces, and several years ago, David Hutchison and I got together and said we should sort of start looking at this systematically to try and understand what's going on. So we define resilience as the ability to provide and maintain acceptable service in the face of various challenges to normal operation. There are a lot we consider, but the ones that we're focusing on are malicious attacks. So these are people that understand the structural properties of the networks, as well as large-scale disasters. And so that obviously works well with what we're doing here. I'm going to start by briefly going through a strategy for designing resilient systems that we have come up with, and then show how it applies to this. So we call a strategy d squared r squared plus dr. I'm going to concentrate on the disaster aspects. So the first bit is this stuff in here, and in the center of the loop, and this is a real-time loop that goes on throughout the network all the time. And first, there are structural defenses. So that is, you want there to be redundancy and diversity and alternate paths, so that if part of the network is taken out, there are alternatives that can use without affecting services at all. And those are these structural defenses in the center. Then actively, we want to defend. So active defenses, ones that people are used to, are things like firewalls that are looking for known signatures. And if the structural defenses and the active defenses hold, great, but of course they won't always. So we need to detect when something is gone. And we're increasingly looking with the folks in China at how to do rapid deployment of replacement infrastructure. So the detection now becomes not merely a problem of detecting when the network goes down, but how it's gone down, what the threats are to first responders. You know, can you get in? Is it flooded? Are there toxic chemicals? So that we can then determine how to remediate, which, among other things, is simple things like rerouting traffic, but is also rapidly deploying replacement infrastructure, sort of a temporary network. Then ultimately, we want to recover back to the original conditions once the threat is gone. Then in the background, we want to diagnose. We want to see what went wrong. This is fault diagnosis, root cause analysis, understand what happened and why. And we want to refine, which is we step back and we look at the entire process, including this inner loop. Did we defend well? How well did we detect? How well did we remediate to evolve the network to be better in the future? There are a set of principles that go along with this, and three of the most important ones are redundancy, diversity, and heterogeneity. So for example, if I got two entities communicating at opposite ends, I want multiple paths, so clearly I want redundancy. I want those paths to be diverse. I would like them to be diverse geographically. That was mentioned earlier. We don't have the information for that now. We're working on a routing algorithm that includes geolocation as part of the link state. But right now, you don't know if your fiber, if you're multi-home to two service providers, if they both go through the same tunnel under Baltimore and melt at the same time. So multiple providers, geographic diversity, diversity in medium. So a wired path, but if the backhoe comes, you can use the wireless, and if the storm comes in the wireless, you can use the wire. We want a way to measure this. It's a complex problem. We'd like a single number between 0 and 1. My network has a resilience of 0.78. Yours is 0.62. Mine is better than yours, but that's complex. So what we do is we model this as a two-dimensional state space. The horizontal axis is the operational state of the network. So normal operation is what the network is designed for. It's where you assume you're going to start. And then as there are challenges, the network degrades. And so a resilient network is one that sort of stays pushed to the left there in the green, even when there are challenges. Users don't care about that. Users care about the service. So that's the vertical axis. So acceptable service to some service specification is where you assume you start if you have a feasible service specification. And then as the network degrades, if the service is resilient, you want to stay low. So the lower you stay, the better. Each of these axes are multivariate, so we have objective functions that describes them. And we can indeed measure and get a number. So if we look at the trajectory from initial state to what happens when something bad happens and there are challenges, we simply can integrate under that trajectory and actually get real numbers. And as we can look at the trace through time, so something bad happens, we get to here, we remediate to make things temporarily better, and then go back. So here's a quick example. Don't take these carriers too literally, but here's an example where we're failing links, layer 3 links, and looking at the connectivity of the graph above, and you can see that some service providers are lower and do better than others. In this case, this is GEONT. It's a European research network. It's not even bi-connected, so it doesn't have a feasible service specification, even when nothing has gone wrong. Over time, then, we start out with some performability. You already saw something like this today. We have a disaster. We assess what needs to be done. We remediate, including rapid deployment of new infrastructure, and temporarily get better, eventually build out and recover back. This is a complex problem because the network is indeed multi-level. So if we just look at one service provider, we've got a fiber map in green, but over that is some sort of overlay like MPLS, and then finally a layer 3. The layer 3 graphs are pretty available as inferred from rocket fuel. The lower layer graphs are harder to get that information. Furthermore, we have interdependence with physical infrastructure, such as highways and railways, where fiber is laid, as well as the grid that's already been mentioned. To make this a little easier, we've developed a tool. So if you Google KU Top View, this data is all online. We've sucked in all the rocket fuel data. We have quite a few bits of physical fiber maps, and you can manipulate them, create adjacency matrices, and then we use that as an input to our tool. Skip the diversity bit, where we have an analytical and simulation-based methodology where we specify a particular network as node coordinates geographically, and adjacency matrix, how are they connected, and then we can overlay arbitrary challenges onto that, push it through NS3, and get results out. So the sorts of challenges we can simulate are things like particular node and link failures. So we can say an attacker who understands the structure of the network may try and take down the links with the highest degree, or the highest betweenness, which is a measure of importance. So we can do that. We can also overlay arbitrary geographic areas. So this is something that looks maybe like an increasing cascade failure starting in the Midwest US. We can do circular regions, which are things like EMP weapons and coronal mass ejections, and we can also have these dynamics. So this is sort of looking like a storm moving up. It's critical that we do it at the right level. So here's a case where we have a very simple simulation of a hurricane around New Orleans growing. If we were to do the layer 3 using the rocket fuel, it would look like in aggregate over time nothing has happened to the network at all because there is no pop in New Orleans for Sprint. But of course, Sprint really has fiber going through, so what we have to do is attack the fiber, do the attack at layer 1, see how things propagate up through layer 3 and layer 4 and the application layer, and then we start to understand the effects of the right sort of a challenge on the infrastructure and how that affects the user. I thought I had something there, sir. Okay, that's it.